Effect of temperature on resistance, conductivity and resistivity. Now from the free electron theory, we have derived that the resistance is equal to M divided by E square N so into L bata A, where L is the length of the conductor, A is the area of cross-section of the conductor, M is the mass of the electron, E is the charge of the electron, N is charge density, and tau is relaxation time. And the resistivity rho is equal to M divided by E square N tau, and conductivity, which is the inverse of resistivity, is equal to E square N tau bata N. Now for the conductor or metals, the resistance will depend upon tau, because mass of the electron is constant, each charge of the electron is constant, and number density for that particular conductor is constant. Tau, which will depend upon the temperature, L and A, both are constant with the temperature. So the effect of temperature will be on the relaxation time. Now what is the relaxation time? Relaxation time is average time between two successive collisions. Now as the temperature increases, what will happen? Number one, the velocity of the electron with free electron will increase. Number two, the ions which are fixed at the lattice, they also start vibrating, and due to the vibration, the frequency of collision will increase. Frequency of collision increase means the time for the collision or two successive collision or tau will decrease. So as temperature increases, tau decreases. Temperature increases, tau will relaxation time will be decreases. So the resistance will naturally increase. Similarly, the resistivity will also increase because tau is less, and the conductivity will decrease because tau is in the numerator. Here tau is in the denominator. Now for the electrolyte. For the electrolyte, the resistance is high. Why? It is because here mass is the mass of ion. Mass of ion is much larger than the mass of electron. Charge E, N, and we have considered all these things, then the resistance of electrolyte will be always higher than the resistance of the conductor. Now we take the semiconductors. In semiconductor, if we increase the temperature, then the resistance will decrease. Here, we increase the temperature, the resistance increases for electrolyte as well as the conductor. But for the semiconductor, the resistance will decrease as temperature increases. Temperature coefficient of resistance and resistivity. Now what do you mean by the temperature coefficient of the resistance and resistivity? If we take RT is the resistance at T degree Kelvin, R0 is reference temperature, and at this reference temperature, we write T0, and T0 is 0 degree centigrade, or we will convert into Kelvin terms. So RT, the difference, the increase in the resistance due to the temperature from 0 to capital T, then the increase in the resistance is proportional to R0. Which R0 is more, then this difference will be. Second, it will depend on the temperature difference. RT minus R0 is also proportional to T minus T0. If we combine these two, then RT minus R0 will be proportional to R0 into T minus T0. And we take proportionality constant as alpha. Alpha is the proportionality constant, and this proportionality constant is temperature coefficient for distance which is equal to alpha. So we can write alpha is equal to RT minus R0 bata R0 T minus T0. This will be the temperature coefficient of conductor. What will be the effect? Because R minus and ohm, R0 ohm cancel. So 1 bata T minus T, its unit will be temperature inverse, or that is either it is the degree centigrade inverse or Kelvin inverse will be the. Now for metals, alpha is nearly equal to 1 bata 270. And for alloys, then for alloys, alpha is more. Why alpha is more? Because in the metals there are same type of atoms fixed in the lattice, and there is a regular arrangement of these. Suppose we take the copper, then the atoms of copper are at a equal distance from each other. So there is a regularity or there is a periodicity in the structure of the atoms in the lattice. But if we make the alloy, if we take a alloy, I gave the example that a nichrome is a alloy. It is made with the nickel, is a +2 and chromium +3. And this alloy is a mixture. It is a mixture, means there is no definite relation or there is no definite proportionality of the nickel atoms and chromium atoms. It is not there. And the size of the nickel atom and chromium atom is also not equal. The periodicity is not good. So the alpha will be very less, and for this alpha will be equal to 0.002 into 10 raised to minus 3 Kelvin minus 1. So the alpha, the temperature coefficient will be very small in the case of this. Hence, if we draw the curve for the metals, suppose we take the copper, then we find a ρ2 with respect to the temperature. Now as temperature goes near to 0, here it is Kelvin, and as temperature is very high, then the relation is linear. But as the temperature decreases, it is a curved one. For alloy, that is nichrome, from the 0 to 800, it is linearly, and the variation is linear. So we will use the nichrome for the preparation of resistance, because number one reason is the resistivity is linearly proportional to the temperature, and the variation is very small. Here the variation is for the metal, here when temperature is very high, it is a straight line. But as temperature decreases, it is a curve, means the relationship is not linear. Now if we take the case of semiconductor. In semiconductor, the resistivity decreases as the temperature increases. So here alpha will be negative. In the case of semiconductor, alpha is negative. For the conductor and for alloy, alpha is positive. Now we take an example to find the unknown temperature of some oven or any body. So for measuring the temperature, we find the resistance. The resistance is found with the help of platinum resistance thermometer. platinum resistance thermometer. So we will use the platinum resistor and we will find the resistance of the platinum resistor at ice temperature means R0. This is 0 degree centigrade. We will find the resistance of platinum resistance thermometer at steam temperature, that is R100. And we will find the resistance for a unknown temperature. Now the value for the R0 means resistance of platinum resistance thermometer at 0 degree centigrade is 5 ohm. At steam temperature means R100 is equal to 5.2 ohm. And for the unknown temperature, the resistance is 5.8 ohm. So from this relation, we write here RT minus R0 is equal to alpha R0 T minus T0. So here RT minus R0 is equal to alpha R0 into T. This is the temperature difference. So R100 minus R100 minus R0 will be equal to alpha into R0 multiplied by the temperature difference is 100 minus 0. 100 minus 0. So this will be equal to 100 times alpha into R0. For unknown temperature RT minus R0 will be equal to alpha RT R0 bracket T minus 0. So this is equal to T into alpha into 0. If we divide these two, then we will get RT minus R0 divided by R100 minus R0. This is equal to T by 100 because alpha and R0 is common. They will be cancelled. So it will be equal to T divided by 100. So unknown temperature T will be equal to, we cross multiply, it will be equal to RT minus R0 but R100 minus R0 into 100. So we substitute the value of R0, RT and R100. Then the unknown temperature will be equal to 5.8 minus 5 divided by 5.2 minus 5 into 100. So this will be equal to 0.8 divided by 0.2 into 100. So this will 4, so it will be 400 degrees centigrade. So temperature of the unknown bath is 400 degrees centigrade. So in this way we can use this relation, the temperature difference coefficient, temperature coefficient for the platinum resistance thermometer, and we can find the unknown temperature. Now this is all about the conductor. Now what is the next term is superconductor. Now what do you mean by the superconductor? Now there are some metals like mercury, aluminum, zinc, indium. These materials are superconducting material. For these metals, which is the mercury or indium or zinc, then what will we find? If we decrease the temperature much less than 0, then the resistance will decrease. If the temperature is decreased, then the resistance will decrease. Naturally the temperature will decrease. So the temperature is decreasing. And I am taking the example for mercury. This is the example for mercury. Now as the temperature is decreasing and temperature is very small and it is in the Kelvin degree, and we find the resistance. That resistance is continuously decreasing but decreasing slowly as temperature is decreasing. But at this temperature, which is 4.2 K, which is known as the critical temperature, the resistance of the mercury decreases suddenly to 0. From this value to 0. And this mercury will be superconductor. Now, what is the critical temperature? Critical temperature is the minimum temperature at which the resistivity or the resistance of the conductor becomes zero. Now what are the superconductors? Those materials for which the resistance becomes zero at the critical temperature, such type of materials are known as superconductor. Now what is the superconductivity? Superconductivity is the phenomenon. The phenomenon is superconductivity. The superconductivity is a phenomenon by virtue of which the superconductor material at the critical temperature, their resistance becomes zero. Now what do you mean by resistance becomes zero? When the resistance is zero, if the electron is moving, it will move for the infinite time because there is no resistance. So if the temperature is less than critical temperature, then this material, mercury, the critical temperature is 4.2. If the temperature is less than 4.2, then their resistance is zero. It will become superconductor. And if the electron is flowing in the conductor, it will flow for the infinite time. Now, we take the magnetic property of superconductor. Suppose this is the superconductor and we put it in the magnetic field. This is the direction of magnetic field. And its temperature is more than critical temperature. When the temperature is more than critical temperature, then the substance is not superconductor. It will behave like a conductor. It will not behave like a superconductor. It will behave like a conductor. And the magnetic lines of force will pass through it. So, total magnetic field will be equal to, V will be equal to VA. VA is the external magnetic field plus induced magnetic field, which is equal to mu into M. So, the total magnetic field will be external magnetic field VA plus induced magnetic field mu into M. And if we decrease the temperature, and when it becomes superconductor, then these magnetic lines of force will not pass through the material, it will be away from it. So here is when the temperature is more than, temperature is less than critical, then here B is not equal to 0. Inside this B is not equal to 0. Now B becomes 0. All the magnetic lines of force will be away from it. It will not enter into this. It will be always away from it. So, at the critical temperature or less than critical temperature, B is equal to 0. So, BA plus mu into M is equal to 0. Or BA will be equal to minus mu 0 into M. It means there will be no. So this property is just equal to the properties of diamagnetic substances. Diamagnetic substances are those magnetic substances which repels by the magnetic field. And this effect is known as the Mechner's effect. MEISS-NER. Mechner's effect. According to Mechner's effect, when the temperature of the substance or superconductor is less than critical temperature, then there will be no magnetic field inside it, or the magnetic lines will be outward the substance. Electrical energy and electrical power. Now, if we have a conductor and we connect it by the external source, potential field, the current will pass. Then the current will be uniformly passing through this. If you take this end A and this end, then the potential of this end A is greater than B. So current will flow from A to B. If VB is greater than VA, then current will flow in the reverse direction. So when the current is flowing flow of current is flow of charge. If we take for a small interval delta t, if delta q charge is crossing some area of cross section, then current will be equal to delta q by delta t, or delta q will be equal to I into delta t. Now, what will be the work done? Work done by the source. The work done by the source will be equal to, we can find the simple method by taking the potential. What is the potential difference? If the potential difference between these two is VA minus VB is V. Potential difference is there. Then what will be the work done? By the charge. The work done charge will be equal to the charge multiplied by potential. Now what is the potential? Potential is work done to bring a charge from unit charge from infinity to next point. So if delta V is the potential difference, delta Q charge fluid, then the work done by the source delta W will be equal to delta Q into V. And instead of delta Q we can write I into delta T. So it will be equal to I into V into delta T. So this will be the small work done for small time. Means delta W is the small time for the charge which is flying from the conductor in delta T time. Now what will be the total work done? Total work done we can find the result, the integration. So total work done W will be equal to integral dW is equal to integral I into V into dt. Here we take delta T as small dt, delta W as dW. As time changes very slowly or tending to 0, we can have this value as dW. Here we can have value dt. Now the integration dW will be equal to I is constant, V is constant, and dt will be equal to time. So work done will be equal to I into V into T. Now by the Ohm's law, we know that V is equal to IR. We put the value of V. Then work done will be equal to I square R into T. If we put I is equal to V by R, then this work done will be equal to V square T by R. So these all relations are equivalent, and this will be the work done. Now what is the power? This will be the electrical energy. Work done will be equal to electrical energy, and this will be equal to IV into T, or I square R into T, or V square by R into T. Now what is the power? Power is rate of doing work, means work divided by time. So power is the electrical power will be equal to the electrical energy quantity time. So V will be equal to I into V. Here if we divide by T, then P will be equal to I square into R. Similarly, P is equal to V square by R. So these are the relations for the power. What will the unit is? SI unit of work is joule, and SI unit of power is joule per second, and joule per second is watt. So this is the energy. This is the unit of energy per second. That is watt. This is the energy, and that is equal to joule. Now what is the Joule's law? If the current is passing through the conductor, or any mechanical work done is done, and due to this mechanical work is converted entirely into the heat. It means the work done is proportional to it. If more work is done, more heat will be produced. If we rub our palms, then if we rub more and more time, then the temperature of palms will be increased more and more. So work done is proportional to heat, and work done is equal to J into H. J is the constant, and this constant is mechanical equivalent of heat. So the value of mechanical equivalent heat is J is equal to 4.2 joule per calorie. the unit of work is joule, unit of heat is calorie. So 4.2 joule J is equal to this. So if 1 ton is suppose if 1 ton is equal to 1 joule, W is equal to 1 joule, then heat produced will be F will be equal to 1 bata 4.2 calorie. And if 1 calorie heat is produced, then how much work is done? H is equal to 1, so W will be equal to, so 4.2 joule. If work is done, then 1 calorie heat is produced. So in this way, we can have a relation between heat produced and work. Okay.